This will be for the con exercise, limits of composite functions. All right, so functions h and f are graphed, and they want us to find the limit as x approaches 3 of h of f of x. All right, so for this right here, the first thing we want to do is find the limit as x approaches -3 of f of x, the function that's inside the parentheses. All right, so we're looking to do this part first. X approaches -3 of f of x, the function that's inside parentheses. All right, so we're going to x equals -3 right here. All right, coming from the negative side, tracing the graph, we land on y equals 1. And coming from the positive side, tracing the graph, we land at y equals 1. Okay, so this is definitely 1. It's the same from both sides. So this right here is 1. And now since this limit was 1, basically what we're going to do at this point is just evaluate the h function at x equals 1. All right, that's all you have to do. The only thing is, the only stipulation is that at x equals 1 on the h function, this must be continuous at x equals 1. Okay, and that's on the h function. Continuous basically means you can draw it without lifting your pen or pencil. So let's go to x equals 1 on the h function and see what this equals. We want to find out, and if it's not continuous, then it's going to be DNE, does not exist. All right, so let's take a look. All right, this graph here is the h function, and we said we're evaluating it at x equals 1. So you can see this asymptote here. We can't evaluate it at x equals 1. Here it goes down to -infinity. Here it goes up to +infinity. So we cannot evaluate h of 1. So that's going to be DNE, does not exist. All right, limit as x approaches 1, h of f of x. We're looking at the function inside parentheses, x approaches 1. All right, so we're going to do the limit as x approaches 1 of f of x. All right, so let's go to x equals 1 right here. X equals 1 right here. Oh, wait a minute. We're just doing it for f. We're just doing it for f of x, so x equals 1 right here. Okay, so from the negative side, trace the graph. We land on y equals 0. From the positive side, trace the graph. We land on y equals 0. So this right here is going to be 0. All right, so since we got 0, we're basically just going to find h of 0. So we look at x equals 0 on the h function. All right, and again, it must be continuous at x equals 0. All right, must be continuous. So let's check it out. At x equals 0, on the other graph, the h function. This one is my h function. This is x equals 0. If we go to the graph, we're at y equals 3. That's it, done. We can see it's continuous here because we can draw the graph without lifting the pen through that point. All right, x approaches -2 f of h of x. So we're looking at this one right here for x approaching -2. The limit as x approaches -2 of h of x. All right, so let's go to x equals -2 on the h of x graph. X equals -2 right there. Okay, and from the negative side, tracing the graph, we land at y equals 1. From the positive side, tracing the graph, we land at y equals 1. Okay, so this is going to be 1, and we're going to evaluate the other graph at x equals 1, and it has to be continuous. So this is going to equal f of 1, but it must be continuous at x equals 1. So this was the f graph. Here's x equals 1, and the y coordinate is 1. Okay, it is continuous because, again, we can draw the graph through that point without lifting the pen. Y equals 1. All right, last one. We're looking at h of x as x approaches 3, the limit as x approaches 3. And that's for h of x. So let's take a look for the h of x graph. We're approaching 3, x equals 3 right here. All right, from the positive side, we land right here, and that's at 2. From the negative side, again, we land right here, that's at 2. All right, so now we're going to evaluate the other graph at x equals 2. It has to be continuous. Here's the other graph, x equals 2 right here, and the y coordinate is 0. All right, is it continuous? Yes. Okay, if not, it would be does not exist. But it is continuous right there. I can draw it without lifting the pen. 0. All right, there you go.